Hi everyone, this is our video for Activity 3. This week we primarily talked about measures of variability or different ways that we can assess how spread out our data is. And then we also talked about the normal curve, which we'll also refer to as a normal distribution, and how that relates to statistical inference when we're trying to relate sample information to population information. So we have a small set of tests that we're going to be running today. Okay, so we're going to start on our student values tab in our Excel spreadsheet. Similar to our last activity, any formulas that you'll need to use during this activity will be listed here. Even if you don't end up using them, they're formulas that we've covered previously, okay? So the goal of this first spreadsheet is to calculate measures of central tendency and variability using both Excel and SPSS. So last time, I think at the end of Activity 2, we kind of dabbled in SPSS a little bit and found that we could perform certain calculations through that program. So we're going to go back in there and kind of mess with different calculations that we can do in both Excel and SPSS. When you take the exam, ultimately it's up to you which program you use, but I just want to give you guys options and then let you decide for yourself. Say hello to butter. That was what the jingle bell was. So basically our scenario for this situation is we have various measurements that have been collected from students in an exercise class, and we're wanting to, let me pop down here, calculate the mean, median, quartiles, standard deviation, skewness, and kurtosis for each of these variables. Okay. And we can do all of these by running a frequencies analysis in SPSS. We wouldn't necessarily need to run a means analysis because we don't have any separate groupings that we're interested in. In Activity 2, we had like male versus female or different sports. When we don't have groups that need to be separated, frequencies analysis is adequate for giving us the calculations that we want. In addition to making these calculations in both Excel and SPSS, the only difference between these two is going to be the quartiles and how we calculate the skewness, but I'll show you guys how to do that. But we're also going to play with making histograms, and there is some small discrepancies in altering information in the histogram. So if you do run into issues, I'll point them out. But if you do run into issues, I can always make an additional video on my HP so that you have a Windows Excel version of altering graphs, because this one is definitely not intuitive on how you would find these alterations. So let's first start with these calculations. I've added some explanations on how different Excel functions work as far as calculating skewness or kurtosis, as well as what you assume about the shape of the distribution based on the values that you get. Okay, so you can always use that area as a reference. We're first going to start by just copying the labels that we have in our original table, and I'm just going to paste them somewhere over here. And then I'm going to make a column that has the calculations: mean, median, standard deviation, coefficient of variation. Okay, so we'll do mean, median, standard deviation, coefficient of variation. Okay. Everybody should remember how to calculate the mean. Right, we do equals, average, and then if we're calculating the average for mass, we just input, right, all of that data. Median we played with last time, right? So you type median, again highlighting all of the data that you want the median calculated from. Standard deviation we've also done before. Okay, remember this is just measuring the general spread from the sample mean, right? And then our coefficient of variation, I included the formula up here. This one we just have to type in, but we can use cell references from our calculated standard deviation and our calculated mean to make this work. So coefficient of variation is going to be equal to, in parentheses, you can put in parentheses, you don't have to. Order of operation should work out. I put parentheses just in case. Okay, so it'll be standard deviation divided by the mean times 100. Okay, let's go ahead and format these so that they are giving us, let's say 1 decimal place. I don't think I specified on the answer sheet. I did not. So yeah, let's do 1 decimal place, and then those are the values that you'll report. Okay. And then pretty much we have these set up so that every time we copy these equations to the right per column, the references should shift per column. Okay. As far as the references for the coefficient of variation, they're not really going to change because we're not copying up and downwards. I'm just going to copy these over, and we now have all of our calculations made for each of our variables. Okay. I also want to show you guys how to calculate skewness and kurtosis in SPSS. As far as reporting, your values in your answer sheet can either come from SPSS or Excel. I just think it's valuable to know how to use both. Okay. So when we're calculating skewness and kurtosis, hopefully, I'm recording this prior to the actual recorded lecture, so hopefully we have a chance and have time to go over this process in the lecture, but if not, the data set that I post with the lecture you guys can use for practice. But basically what we need is the sample skewness value. Okay, we will have some standard error of skewness. So I'll just put SE skew, and then we're going to use that standard error along with the sample skewness to get a z-score of skewness. And the z-score of skewness is our standardized score so that we can basically evaluate if our sample distribution is relatively normally distributed in comparison to the population, which we assume is normally distributed. Okay, so we basically just have to show that our sample distribution is similar enough to the population distribution, which is normal. So that's why we run skewness and kurtosis calculations. So I'll have sample one area for skewness, and then we'll basically just create the same labels but for kurtosis. Okay, and then we'll have a z-kurt. Okay, we'll do this for each of our variables. So I'm going to make skewness, actually, I'm going to make skewness just so these are a little bit more separated, and you guys know I love color. I'm going to make skewness green, and I'm going to make kurtosis blue. In addition, because borders are not identified, I'll add some borders for you guys. The main thing to remember is that your z-skew and your z-kurt rows are going to be the ones that you use to evaluate if a certain variable is normally distributed or not, right, based on the sample data. So in order to calculate sample skewness, all we have to do is we type equals and we type skew. You'll see two functions pop up. You just want to use the regular skew one. Okay, and then it's asking for a number. Basically, you just put in the cell range. So if we're calculating the skewness for our mass data, you just highlight all of that and pop it in there. Okay. From here, we can calculate our standard error of skewness. I've also included this in here. So again, whenever we compare any sample data to a population, we usually have to divide some sample information by the standard error, which standard error is similar to a standard deviation in the respect that standard error just tells us where our sample average is from the population average. Okay, so you can either, it's completely up to you. If you're calculating in Excel, you can merge this calculation into one box, or you can separate them. I like to separate them because I think it shows a difference between Excel and SPSS. Okay, but it's ultimately up to you. Okay, the standard error we calculate is represented by the denominator of our z-score of skewness function over here. Okay, so in order to get the square root part, we just type SQRT, right? Square root makes sense, right? Put parentheses so we enclose this information. And then we divide by 6, square root of 6 divided by the total number of observations that we've collected, or however many people are in our sample. So if you remember from last week, we can use a count function, and that'll just return the number of cells that have values in them. Yes, that's just telling me to close my parentheses. So I don't like all of these numbers, so I'm going to correct these decimals. Let's say to 2 decimal places is good, but it's just really overstimulating. All right. So once we have this information, you can see in our z-score of skewness formula, we take the sample skewness and divide it by the standard error, right? So all we have to do is type equals sample skewness divided by, and a lot of times this happens. If it does, just hit the up arrow and you can see that this standard error box has now been highlighted. Okay, you press enter and we end up with our z-score of skewness. Okay, so now you've kind of formatted that. As you drag across, right, it'll copy your cell references for each of these respective rows. And you have done a mass calculation, which should feel so good. All right, so that's for skewness. Then we can calculate for kurtosis. So similarly, for the sample kurtosis, it's just equals kurt. Okay. Again, working out of the mass column, we're just going to highlight all of the values. Standard error for kurtosis is kind of similar to skewness, but the numerator is different. Okay, so we're still going to put the square root. But if you look over here in the Word document, the numerator is 24. Okay, these are constants, so you just literally just type in the number. Okay, and again, we're going by the count of however many values or cells have values in them. Yes. Okay, from here, similarly to z-score of skewness, we're just going to take our sample kurtosis divided by our standard error of kurtosis, and that will give us our z-score of kurtosis. Okay, again, we can copy all the way across. Okay, so basically what we're looking at is whenever we have values from the sample that are placed on the population, if our sample is outside of 2 standard deviations from the mean, that's plus or minus 2, right, of the mean in the population, then that means we can assume our sample is similar enough to our population, right? Because again, standard error is just looking at some sample average and where that lands in the population distribution. So if a population distribution is normally distributed, we would expect there to be few outliers or few sample points in the outer regions of that distribution, which is usually between 2 and 3 standard deviations. So if we have too much data out there, then we're not really representing what the core of the population would be, and that would be between 2 standard deviations, plus or minus 2 standard deviations from the population mean. So this is kind of how we set the criteria for if we determine if a sample is skewed or kurtosed, right? And then based on the sign of that z-score of skewness or kurtosis, we can say if it's positive or negative. So this is where the criteria comes in. If you have a z-score of skewness or a z-score of kurtosis that is between plus or minus 2, we say that the sample distribution is relatively normal because this value represents where our sample would land within a population distribution. Okay. If we have values that are less than -2, so they're getting more and more negative, or if we have values that are greater than +2 standard deviations for both skewness and kurtosis, we say our negative values represent either negative skewness or negative kurtosis, and our positive values represent positive skewness or positive kurtosis. Okay, now it's a good reminder to think about values that might be very closely approaching -2 or 2. Basically, we usually are just going to say, like, this is a great example, right? You have -2.02. And then you're like, well, is it close enough to 2 that we could say it's still normal? Or is it far enough out of our boundaries that we're saying it's negatively kurtosed, right? In our class, -2 and +2 are hard stopping points, right? So anything past -2 and anything past +2, we would say are positive or negative skewness or kurtosis, respectively, okay? So this is how we calculate these things in Excel. I personally like to use Excel because SPSS, you have to format all of your variables, but for the sake of practice, we're going to do that in SPSS anyways, okay? And I'm going to go ahead and do the calculations in SPSS first, and then we'll come back and we'll make the graphs. So if you don't already have SPSS open, you can go ahead and open it. And then basically what we're going to do, if you remember the layout in SPSS, each row represents a specific individual, right? So each row should contain the data points for each individual that has been measured. This one should be pretty easy to copy and paste into SPSS. So we're not going to worry about the student ID part. We're just going to copy all of our data with our labels. In SPSS, make sure, again, you're in data view. You can paste. I just screwed that up. Make sure you two-finger click or right-click, paste with variable names. And you'll see we have like a little ruler that indicates that these are all listed as scale or ratio data. Okay, so again, that's the default, but if you wanted to go into variable view and make sure that they're listed as scale, you can do that. Okay, from last week, you'll remember to get to a frequencies analysis, we go from analyze to descriptive statistics to frequencies. And then you're going to go ahead and just insert all of your variables. And you're going to click statistics. In our instruction sheet, I asked for mean, median, quartiles, standard deviation, skewness, and kurtosis. Okay, so quartiles, this was just mainly for an example for you guys to see a quartile calculation, since we've kind of covered them a little bit more now in class. We'll do mean, median, skewness, kurtosis, and our standard deviation. I think I got everything. Okay, so you go ahead and click continue, and you press OK. And then we get our calculations. Okay, you can disregard the frequency tables for all of these. Okay, but this first box is primarily what we're going to be looking at. So you can see the mean is calculated across here, and I mean, if we wanted to, we could see. I'm gonna resize these here so we can look at everything, right? The mean for mass is 77.8 kilograms. Whoa, that's what we calculated here, right? So you can kind of double check your work between SPSS and Excel to make sure that your calculations gave you the same values. Okay, now in SPSS, your skewness and kurtosis values will oftentimes come out slightly different than what you get in Excel, but usually it's by a couple of decimals. So more often than not on exams, the answers I put into the quiz questions are going to be out of Excel, but I hand grade all of the exams question by question. So if something is marked wrong, I usually double check it to make sure that, like, oh, if your answer was close enough to the value, and I can assume, like, oh, maybe they just use SPSS or they had some type of rounding error, you'll still get points if it's if your answer isn't exactly matching mine, but if it's close enough. Okay, so a cool thing that we can do in SPSS is if you double click on any given table, you'll notice that there's like a dotted box that comes up around it. This will allow you to highlight certain portions of the table. And what I really wanted to show you guys is highlighting the skewness and kurtosis stuff. So if you didn't want to go through all of the hand calculations in here, which really isn't a lot because you're only calculating one column and then just copying everything over, but if you didn't want to do those calculations in Excel, you could pop them into SPSS. The thing you have to remember is you still have to calculate the z-score of skewness and kurtosis with the numbers you get in SPSS. So if you double click on the table, highlight the skewness and kurtosis values, you can copy and then paste them into Excel. Okay, and a lot of times you'll have to reformat. I'm just going to make these values a little bit bigger so it's easier to see. Okay. With this, if you highlight a given area of cells, you can insert by shifting the cells downwards, right? And then you can add this z-skew, right? Which should program, again, taking the sample skewness divided by the standard error to give you a value. And again, you'll notice, see, these two values are just slightly different by 0.05. Okay, so again, if your answer is relatively close enough to what I have recorded in my answer key, then you're honestly fine. Okay, but since we already calculated these and the cell references were set, I copied and pasted. Obviously, you're more than welcome to hand insert these calculations over again, but this is just to show you what numerical discrepancies may exist between SPSS and Excel, and how to get these calculations through both platforms. Okay. So with that, I'm going to just minimize my SPSS windows, and I'm going to go back to our instructions. So now we're going to make some histograms based off of mass and VO2 variables. Okay. Histograms are really cool because they put your data in bins. So if you remember in our group frequency distributions, we have these intervals, right, of XX units, right? And intervals in our group frequency distribution are equivalent to bins, basically, right? And bins are, you can set the interval width, you can set how many bins you want, and then see how the interval width changes. This will make a lot more sense once I start doing this process. But basically, we're just going to start with mass. So you can highlight all of that data. And then we're going to go to Insert. And you're going to choose histogram, which is the blue columns. Okay, so not a bar graph, histogram. Okay, if you're operating in the Office Excel program through like your single sign-on, you might have a problem with histograms. They've notoriously caused issues with students in the past, and what I'm going to do in here is just make this bigger. And if you click on the entire chart, a cool thing you can do is increase your font size for everything. For some reason on this particular spreadsheet, the graphs come out super small, and I haven't been able to figure out how to fix it. All right. So typically, we always have a vertical and a horizontal axis title. Might suggest adding those before you adjust the font size, but we'll just do it again anyways. Again, chart titles can be super basic, so I want to call, I want to call this one mass graph number 1. Okay. On the bottom, we have a representation of mass, right, in kilograms. And then over here, we have frequency, right, or how many people that we measured fit into each of these grouped intervals. Okay, so from here, we have specified that you want your graph to have 5 bins or 5 columns. You'll notice this automatically generates 6 columns. Not what we want. So, 2 differences. In MacBooks, you will double click on the bars in the graph to format your bins. In Windows, I am very confident that you double click on the x-axis to format your bins. Okay, once you get to that formatting toolbar, which should be over here, you should have the same view of what I'm clicking on. Okay, so again, MacBook, you double click on the bars. Windows, you double click on the x-axis. So you'll see right here it says the bins are on auto. What we want to do is switch it to set to number of bins. So I can specify I want 5 bins total. And then you'll notice these numbers down here, right? They change based on how many bins we have. So this is based on the smallest value in our grouping and our highest value in our grouping, okay? And that's how we generally get these boundaries. They're not just like random arbitrary numbers, okay? The easiest way, right, because we're graphing the same data, is we basically can just copy and paste this graph. So now we have, now we have 2 graphs. All you have to do is change this graph name to mass graph number 2. Again, this one's going to have 10 bins, so you'll just double click either on the bars or on the x-axis if you're Windows, right? And again, it's set number of bins, so we just change it to 10. Voila, donezo, right? And you don't have to add axes, you don't have to add like the titles or anything. Super easy. Okay. If you want, you can reformat or make this graph wider, and that should allow the diagonal axes labels to fix themselves. I really don't care, so if they're diagonal, it's totally fine. Okay. You're going to do this same process for the VO2 max data. Okay. So that should be pretty easy, right? You just highlight all of the VO2 max data, insert histogram, right? And then you'll follow all of the same procedures that we just used for the mass data. So you guys are going to do VO2 on your own. Okay. Now, I want to pop in, because this is pretty much all that you're going to do within the first spreadsheet. I want to go to your answer sheet. Okay. From Excel, you're going to insert various information, right, based on like calculations that you made. Okay. Part C is saying which measure has more variable or more variability in its data set. So on this one, which variable, right? Mass, height, GPA, VO2, or bench 1RM. Which one of those variables has the most variability? So in part C, you'll list the variable. In part D, you're going to list which calculation you used to assess variability to answer part C. Okay? And also list why you chose the calculation you did. Okay? The last part, other than copying and pasting your Excel graphs into your answer sheet, is going to be writing down or recording what the size of the interval is for each of the 4 histograms. Okay, so mass, this is going to be the 5 bin interval size, 10 bin interval size, and then same thing for VO2. Again, how do we calculate interval size? We can use this knowledge from our group frequency distributions, right? So I'm going to put 5 bin and 10 bin, and then we're going to put mass and VO2. Just remember when you're recording your answers that you're reading downwards and not sideways. In previous semesters, I found a lot of people were like, I just made a table. Mass 5 bin, 10 bin, but the way that it's organized and the way that it translates into the Word document, usually people end up putting mass 5 bin here and the 10 bin number here when this is actually the 5 bin interval size for VO2. So just be careful when you're translating your numbers that you're putting them into the right space in your answer sheet. Okay. Basically, the way that we're going to do this, if you remember, calculate interval size by taking the difference between 2 adjacent lower bounds or 2 adjacent upper bounds. Okay. If you decide to use different intervals or different bars in here, you might get a slightly different number than mine, but because that's just how Excel automates its bin intervals, but it's really okay. So I'm going to use the first 2 groupings. Okay, so all I have to do is say equals. I'm going to use the lower bound. So in this bin, the lower bound is 74.9. And then I'm going to subtract an adjacent lower bound, which is 73.4. Okay, and I now have the interval size for my 5 bin mass graph. Okay, so each of these groupings is based on basically like 1.5 kilograms. Okay. Do the same thing for the 10 bin graph. So again, take 2 adjacent groupings and you just subtract lower bounds or you subtract upper bounds. Okay, so I'm going to do lower bounds again. In this case, we have 74.2 minus 73.4. Okay, and so now you can see in the 10 bin grouping, right, more groups should mean that our interval size is smaller. So each interval is basically telling us how much data lies within 0.8 kilograms. And we can evaluate the shape of the distribution, right, as it relates to our skewness, right, and kurtosis. Okay, so remember, this is representing slightly negative kurtosis, or I'm sorry, slightly negative skewness, but it's not less than -2, meaning we're still within the bounds where we would consider this distribution relatively normal. But if we have slight negative skewness, remember the tail is on the side where our negative standard deviations would be. So that means our mean gets drawn to the left or towards the tail, right? And then you can see this kind of like is a little bit further exacerbated in this particular graph, where you actually see this low frequency of outliers at the end. Remember, kurtosis is also a measure of tail activity, but it's mainly looking at, are the frequencies in our distribution relatively quote-unquote normal, where we have a low amount of, or a low frequency of data points on the outer ends or on the tail ends of our distribution, with a majority of our data points in the middle of our distribution, right? So we can evaluate kurtosis. In this case, mass has a kurtosis of negative 0.52, which is relatively close to 0, meaning that we don't really have much kurtosis in this particular graph, right? So the tails, we have lower frequencies on the outside. The reason we probably have this 0.5 is due to a higher frequency in the tail on the right end of the graph. But that could be also due to some of the outlier values that are on this side. So if we took away this grouping in total, right, the frequencies in our tails would be relatively the same. If we had frequencies where in our tails where they were up here, right, closer to what the center of the distribution frequencies look like, that would be more of an example of positive kurtosis, where the tails float upwards, okay, meaning you don't have a few frequencies of data points in the tail areas. Okay, so that kind of summarizes what you're doing for the Excel portion. Okay, in the SPSS portion, you're kind of going to use the answers that you got for your skewness and kurtosis, and then indicate what those values mean, okay, or what those values indicate about the shape of the distribution of the data, okay, which I kind of just explained with a different variable. So use your critical thinking skills and translate to a different variable. You guys are smart. I know you are. All right. Enough of this first one. That was a lot of work. Let's go to PE class. Again, I don't know why these spreadsheets are so small. I have tried reformatting them so they look different. No luck. Okay, so PE class, again, we're going to be working in SPSS. Primarily just letting you guys practice with formatting the data. Okay, so in this spreadsheet, we've recorded the number of laps run per student per class period of a PE course. And we're going to be using a frequencies and a means analysis to calculate mean, standard deviation, skewness, and kurtosis. Okay, so using these two analyses to evaluate the shapes of the distributions. Okay, and I just wanted to show you, really you could use one or the other. Include both of them in the output you submit to Dropbox, but I just wanted to show you guys it's possible to do it in either one. All right, again, the first thing we have to recognize is that when we copy data into SPSS, each row represents a different person. Okay, So the way that our data is set up right now is we have, or we're assuming at least, that there are different people in each class period, right? So if this data set was input into SPSS the way it is, SPSS would say the person in this row, they were measured 1, 2, 3, 4, 5 times, which is not the case. So when we have different groupings, similar to what we did in the last activity, is we have to add certain data labels for our individuals. So let's say for first period, we're going to label everyone in this grouping as 1, and I'm going to correct that there. Right, we're going to insert data labels for second period and label them as 2. Same thing for third period. Again, you'll have to correct your labels. We'll do the same thing for fourth period. And we'll do the same thing for fifth period. So now we have each individual associated with a certain data label, and that will be how SPSS recognizes them as different people. But you'll still notice that all of these values are in the same row. So SPSS would just think, oh, now you just added another value, which is not what we want. Okay, so I'm going to make a legend over here where we're saying class period 1, 2, 3, 4, 5, right? And those labels are associated with first period, second period, third period, fourth period, and fifth period. Okay, and then what we want to do is make a new table where we have the period or the grouping that a person is being identified with, and then the actual data we collected on them, which was the number of laps run. So we'll call this number of laps. And then basically what we're going to do is we're going to copy and paste all of our data over here. Okay, so that's first period. We're going to take second period and put that at the bottom of first period. Insert SpongeBob scene cut 2 hours later. You can laugh. I won't know if you're laughing, but I'm dumb. You can totally laugh at that. I'm really hoping that activities are honestly like one of the best parts of your guys' week, because I have to fill a lot of dead time when I do stuff like this, and that's usually when I say the dumbest things. Okay, so let's say we've got all of our data inserted here. You're going to copy and paste this new table. Again, you can include your data labels. Okay, whee! All right, and then I'm going to go to SPSS. You'll notice that we have a data set already existing. If you want to save this as is, you can go ahead and save it. If not, you can delete the data. I'm going to make a new data sheet. It always does that, which is really weird. I don't understand why. But anyways, we're going to make a new data sheet. I'm going to paste. Right, so I have period and number of laps. Remember, the default for variables is that they're going to be listed as scale. So in this case, we need to go into our variable view. And one, we need to identify what these period numbers mean, right? Because they're not actual ratio values. Rather, they're ways that we have categorized our subjects, right? So we have a label of period, and we have certain values that mean certain things or represent certain categories. So value 1 represents first period, 2 represents second period, 3 represents third period, 4 4 represents 4th period. 5 represents 5th period. So we have now told SPSS, whenever you see these numbers within this certain variable column, you're going to treat them not as data values that have been collected on people, but rather a way of recognizing a grouping of people. And if we are grouping people, it's not scale or ratio data, it is nominal data, right? Because nominal data is our categorical data. And then we have to identify number of laps being scale data because this is ratio data, right? All right, so I'm going to move this over now that we've done that. So the first thing we're going to do in here is run a frequencies analysis for both period and the number of laps to find the mean, standard deviation, skewness, and kurtosis. Okay, we're also going to make histograms in SPSS so you can see the charting abilities of SPSS. Okay, so again, when we go in here, we can go to Analyze, do our descriptive statistics and frequencies. Go ahead and put both of these in here. In this case, we can keep the frequency tables, that's fine. But our statistics are what we're really concerned about. Okay, we want mean, standard deviation, skewness, kurtosis. And then in charts, you'll notice you can make bar charts, pie charts, histograms. Let's go ahead and make a histogram. And then you can also click on Show Normal Curve on histogram. So this will kind of put a little outline of a bell curve in the actual histogram that's made for you, which I think is pretty helpful because I think we visualize a smooth curve better than a stick one. Okay, so you just click Continue, OK, and you now should have the frequencies output, right, added to your big output. Now, one thing I wanted to show is later in this semester, we're going to be running a lot of the same types of tests, and you'll notice it just labels it as the type of test that you ran, which can get really confusing if you can't remember where you originally ran the test. So this first one we ran in our student values spreadsheet, and the second one we ran in the PE class spreadsheet. So a thing that you can do is if you click on the title, right, in your output log, you can name this one student values, and then we can name this one PE class. So that way when you go back, when we have output sheets where you're just scrolling and scrolling and scrolling in this log area, it's a lot easier to locate your tests. Okay, so we could put PE class because we're doing 2 tests on this one. We'll call this one PE class frequencies. Okay, and then you'll notice we get our statistics. Remember, if we were actually using the skewness and kurtosis values, we need to divide the skewness by the standard error in order to get the z-score of skewness or the z-score of kurtosis, respectively. Okay. So this will give you your frequency tables, right? So we know how many people were present in each period. Number of laps, that's why I was kind of hesitant to show the frequency tables, but anyways, you can kind of skim over that part. Histograms. So this is, again, a nice way where we can see these are organized by period. Okay, so period 1, again, this is just a frequency distribution. So period 1, it shows a frequency, I think this was what, like 38, right? So these bar values should match the frequencies that we see in this table. Okay, 38, 50, 48, 38, 35, right? So we relatively have about the same number of people in the class. And you can see that there's this normal distribution curve that kind of is overlaid on top of the graph. Okay, we also have a frequency distribution for the number of laps run. So again, if we took like, oh, someone ran 1 lap over here, and how many people were able to run 1 lap, okay? So that's what comes out of our frequencies analysis for this PE class data. If we go back to our data set, okay, and you can also, if this is the last active data set, you can also run the test from the output, but for consistency, okay, we're going to go to Analyze. We'll go to Compare Means for our means analysis, okay. Remember, in this case, you have to identify an independent variable and a dependent variable. You'll notice most of the time in our class, our independent variable is the nominal data, dependent variable is the ratio data. So means analysis will split up these groupings and let us know, like, what was the mean number of laps run in period 1 versus period 2 versus period 3. Or we could look at different calculations, right? So in this area, we're asking for mean standard deviation and then our skewness and kurtosis. So we can get rid of number of cases. We don't need that. But we do want skewness, and if you hold shift, you can highlight all of these and then put them over here. Okay? All right. From here, I put in this optional area where you could make various graphs if you're a visual learner. You don't actually put these in from the means analysis. So if you click OK, run your means analysis and then rename it PE class means, okay, you end up seeing this is the total number of people we've collected in all of our class periods. So it's 209 students total. But you'll see that now our groupings, right, have been divided based on where our students actually were measured, right, in whatever class they were in. Again, if you're calculating skewness and kurtosis for these different class periods, remember you have to take the sample value divided by the standard error value to give you the z-score of kurtosis or skewness, and that's how you evaluate if the sample actually matches your population. Okay? So if you're a visual person, we can make graphs. Okay? We would do this by going to graphs. I gave you the little flow part right here. So we can go to graphs, and then you put compare subgroups. Okay. So I put in here, you identify subgroups and variables to plot. So our subgroups are going to be defined by our period. Our variables to plot are going to be the actual numbers of laps. Okay. Let's see. We go to options then, and you'll see in here you can do colors or patterns, right? And then you've got different histogram shapes that you can do. So one, the area will show the area under the curve, right? If we were looking at a normal distribution, it'll show the area under the curve. If you do bars, it'll show something similar to what we just got in the frequencies analysis. And if you do a kernel smoother plot, this will kind of show a smooth line that ends up actually being a little bit more jagged based off of what you're trying to create. So that's what this part means. Options gives you the options of what graph you want to put in. I like the kernel smoother ones. So I'm just going to click OK, and this should hopefully come out the way that I want it to. Okay, so we come in here, And you'll notice that we get all of these graphs, right? So this would be first period distributed, and you can see in the back this white smoke color. This is all of the data put together. So this would be periods 1 through 5, right? So you can compare this blue graph to what the sample graph would look like. So this is kind of an interesting comparison of how we would evaluate a sample within a population. In this case, you're taking a smaller sample and evaluating it in a bigger sample. So essentially, it's kind of the same thing, okay? But within these different visualizations, you can see, right, that this first period kind of looks like it's slightly negatively skewed, but possibly relatively normal. And in order for us to make that evaluation, we would actually have to look at the calculations of skewness and kurtosis. Period 2 is probably, I would say based on the shape, you can see the frequencies on the outside, so tails rise up, right? That would be an example of positive kurtosis. Okay, but we also have like a multimodal distribution where it's a little bit inverted of what its actual shape should be, right? Period 3 shows us a little bit more of negative kurtosis. Sorry, Siri's trying to talk to me. We get a negative kurtosis where we have hardly any tails at all, and you can see this white smoke out here, right, is where most of the outliers would be in our big distribution of all the data, right? But we can kind of look at these histograms and you get the relative idea of what you should expect just based on the shape, right? And when we look at shape, we calculate skewness and kurtosis. So that's why those calculations are so important when we evaluate the shape of the distribution, hoping that it'll be normally distributed, okay? So those are some options that you can do. It's not required that you include these, but again, I find that a lot of people who come into this class are visual learners, and the graphs typically help. Okay, I'm going to go ahead and minimize both of these. And we're going to go to our next chart or table. Okay, so in this one, we are going to be calculating percentiles based on z-scores. Okay, so we've collected some data on lung capacities for males and females who are healthy, wheezing, or have COPD. We want to know what percentile each of the following individuals falls under based on their gender and their diagnosed health status. Okay, so our procedures, you can use Excel or SPSS. I don't care which one. I'm going to do an example in Excel, okay, just for the sake of time. You're going to find the mean and standard deviation of each of the 6 groups, okay? And then you're going to use these scores to estimate the percentiles of these people, right, based on their gender and health status, okay? So the easiest way we can do this, because all of this is just jumbled up, is we can add, you guessed it, filters, right? So we can do this by going to Data and Filter, okay? Click somewhere in this data area, and we're going to sort our information. First, let's sort by gender, and then we're going to sort by health status, okay? And now we've magically organized our people. So 1 is female, right? So we have all of our females, and they're organized first by our healthy people, followed by our wheezing people, right, value of 2, and our COPD people, value of 3. And then respectively, our males are labeled as 2, and our health statuses 1, 2, and 3. Okay, so again, the first thing that we want to do is calculate averages and standard deviations. I'm going to do different tables, I think, for each of these. So let's do the means first. and we're going to do female and male, and then let's do healthy, wheezing, and COPD. Okay, so this will be our averages. Okay, if you want to copy, and paste the same table, but just call it your standard deviations. Super easy, super cool. Okay. All right. So again, to calculate averages, we're going to put equals average. This first box is representing the average of healthy females, right? So we have females labeled as 1, healthy, right? I'm getting these from over here, by the way, if you didn't know that already. So we basically want people with a combined label of 1, 1, right? So we want average of lung capacities. And I'm going to stop here because if I go down further, I'm going to start getting into the wheezing people. Okay. I can then calculate the average for wheezing females, so that would be labels 1, 2. Okay, and then I can calculate my averages for COPD females, which would be labels of 1, 3. Okay. We do the same thing for males. If you wanted to copy the formulas, you can, but in this particular spreadsheet, I find it's easier to just type everyone in because the cell ranges are kind of funky. But hopefully this is making sense to you guys as I'm clicking through. I can't spell. Okay, last one will be 3 or 2, 3. Okay. And then what you can do from here is just copy and paste. Do I want to do that? Oh, I take it back. I don't like it. You can, if you might have caught on what I was trying to do, but it's okay. We'll just calculate standard deviations for each of these groups and be done with it. Okay, COPD. Again, males will be labeled with a 2, healthy being 1, and then we'll do 2, 2, and then we'll do 2, 3. Okay, so now we have all of our calculations for our people. Why do you, oh, forgot the D. There we go. All right, so now we have our averages and standard deviations calculated. And then we want to calculate the percentiles for these certain individuals. So I'm going to copy down their information here. We have Jane, Jose, and Janice. Anyone a fan of Friends? Oh my god. Anyways, we want to list what their lung capacity is. Ha ha ha. I know like most people are office people. I couldn't really get on board with the show. I watched the whole thing, but didn't really resonate with me. Alright. Anyways, we have their lung capacities. Okay. And then we're wanting to calculate their percentiles, right? Based off of the gender that they're in as well as the health status they're in. Okay. So we're going to calculate percentiles using z-scores. Okay. And I want you guys, if you don't remember, you can come back up here and you can see that we calculate a z-score by using the raw score of interest minus the mean of the sample from which that person is drawn divided by the standard deviation of the sample from which that person was drawn. Okay, so I'm going to change, this lung capacity is basically our X value, right? And we have averages and standard deviations. So we need this information to calculate the z-score, and in turn, we use a z-table to find out what the percentile of that person would be. Okay? So to calculate the z-score, we're just literally going to type in this formula in Excel. So it's going to be our raw score minus the average of the group from which that person came. So if I scroll back down, Jane is a healthy female, right? So her mean, or the mean from which she's being compared, is healthy females. And then we're going to divide by the standard deviation of healthy females. That'll give us a z-score we can see of negative 0.46. Okay, so we'll do the same thing for Jose and Janice. Jose is considered a wheezing male. So again, it's the raw score minus the average of the group from which that person came from divided by the standard deviation. Okay, and we'll do the same thing for Janice, female COPD. Oops, raw score first. Ha 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 ha. Alright, and then we'll divide by her standard deviation. So now we have our z-scores for each of our people. Okay, we can go to our z-table, fanciful z-table, which I just realized I forgot to open before I started doing this. So we'll do our z-table. Right, and if you guys remember, the way that we read this is the first two numbers in our z-score are read in this column, and then the 100th space of our z-score is read across the top. So for Jane, she has a z-score of negative 0.46, so we're going to be in the negative z-scores, right? And she's at negative 0.4, right? And then we have to count 0, 1, 2, 3, 4, 5, 6, okay? So her probability, right, associated with getting her given raw score in her sample is 32.28%, or 0.3228, okay? There we go. Okay. Same thing goes for Jose. He's at negative 2.6. We could round 7 up to 8. Okay. So negative 2.68. Right? Negative 2.6. And then we scroll over in that row to 8. So his probability, right, or percentile, would be this number times 100, right? So it's basically 0.37%, right? And then if we look at Janice, her z-score associated with her raw score is 1.0. Again, we could round the 9 to 10, so let's just say 1.10. So we'll have to go to the positive score sheet, right? 1.10 would, oh my god, that would put her at a percentile of 86.43%. All right. So what now? What do these numbers mean? Okay. And I have a follow-up question in the answer sheet to get at this. Okay, so first you're going to list what these people's percentiles are. And then you're going to evaluate based on those percentiles, who do you think should have a different health status than what they were diagnosed with? Okay, and this largely is kind of coming back to our empirical rule, where it's saying that 95% of our data that's collected should be within 2 standard deviations, right? So a lot of the times, anything outside of plus or minus 2 standard deviations from the mean means that we have an outlier present, right? Or in this case, if we're measuring somebody in a healthy category and they have a super, super low percentile, right? Maybe their lung capacity is low enough that they need to be put in a different sample of wheezing or COPD. Okay, it kind of just depends on how severe it is. But because we're evaluating each of these individuals and their respective samples, these lung capacities are representative of where they land in their given sample distribution. Okay, so you're kind of evaluating based on these percentiles that we got for each of these individuals who have these lung capacities. Are any of those individuals, do you think any of them have been misdiagnosed, and why, right? Or what health status should that person be in based on the percentile that they got? Okay, so that'll be your critical thinking question for this activity, at least the first one. Okay, the last, we made it. The last spreadsheet is our powered data. Okay, so I'm going to go back to our instructions. And the goal of this one is using different methods of calculating percentiles. So if you remember, we calculated percentiles using a frequency distributions last time, either simple or grouped, right? And in those, remember, I specified that if you are using a frequency distribution calculation, so if I scroll back up, this would either be one of these top two if you have a simple frequency distribution versus a grouped frequency distribution. These are percentile calculations for a sample, right? So if you're looking at a person's raw score, or if you want to know what percentile lands at a given raw score, that is confined to that sample. So when we ask for an exact percentile within a sample, right, given a certain raw score, it is only within the sample that that percentile applies. If we are asking for an estimated percentile, that's usually saying if, let's say, we had all the information that we needed to know about a given population, okay, what would the percentile be given a certain mean and a certain standard deviation, right? And this is within a population. So we're it's kind of a word association game you guys have to play when you look at questions that I'll write for you in your exam, because this is one thing that trips people up all the time. An exact percentile is going to be a score within a sample, right? And an estimated percentile is going to be a score, right? And you're trying to find what percentile that score exists at within a population. And in this particular example, we're going to assume that our entire data set is representative of the population, and it's mainly just to prove a point on how distribution shape can change different results or different calculations that we try to make. So the first thing that we're going to do is we're going to estimate, we're going to calculate the exact percentile of the sample, right, within the data gathered for a person with a peak power of 801 watts. Okay, how do we collect a percentile, right, within a sample? First, we need a raw score, right? If we come back up here, we need a raw score, and we need to know what the cumulative frequency is at that given raw score. Now remember, cumulative frequency just means the number of values that performed at or worse than your given raw score. Okay, so in this case, we don't really need to make a distribution table because we have a way of figuring out cumulative frequency without a distribution table. And then the last thing we need to know is the number of people or the number of data that we have collected. Okay, so I'm going to put this as our exact percentile within a sample. Okay, so assuming that this whole data set is a single sample from a population. Okay, gonna have to use your imagination here because when I switch, hopefully it doesn't get confusing. Okay, but an exact percentile within a sample population, we need to know a given raw score, we need to know the cumulative frequency at that score, we need to know the total number of people who have been collected, and then we can get our percentile. Okay, so the given raw score is 801. All right, and our cumulative frequency, remember, is the value that is, or the number of people who have performed at this raw score or worse than this raw score. Okay, so we're going to put equals, and the way that we can find this out is using a COUNTIF function, right? Our given range is all of this data, okay? And then our criteria should be, we want values that are equal to or less than, because power output, the larger the number, the greater the power output, smaller the number, the lower the power output, right? Which in our case, the lower value is kind of our worse than end of the spectrum. So we want all the values that are equal to or less than and match our raw score of 801. Okay, so I just arrowed up because this box blocks my row above. Okay, so why did you not love me? Maybe it wants me to do less than or equal. There we go. Less than or equal. My bad. All right, so we end up having 55 values that performed worse than or equal to 801 within this sample. Okay, if we want to know the total number of participants that we've collected, we can use a count function, and that'll tell us how many cells have values in them. Okay, so we're out of 258 people. Our percentile then for this sample would say this person who had a raw score of 81, right? 55 people performed at or worse than that score, divided by the total number of people who we collected, which is 258, right? And then we're going to multiply that by 100. So we have a percentile of 21.32. Okay? So again, assuming that this data is representative of our sample, we can say at a given raw score within this sample, a person who has 801 power output, right, is at the 21st percentile, approximately. Okay. If we wanted to estimate the percentile for someone with a power output of 801 within a population that we're assuming is normally distributed, okay, how would we do that? So again, sample, usually you're going to be using this method, right? Or if it's a grouped frequency distribution or grouped sample, you'll use that respective formula. But for sample, distribution method, if you're looking at a percentile for a population or trying to infer some raw score from population, we use z-scores. Okay, because z-scores are a way that we can standardize our measurements such that we're incorporating some type of standard error measure into our formula, and that tells us where our sample data would land within our population data. Okay, so this is going to be my estimated percentile within a population. So in this case, because we don't have population data to work off of, we're just going to assume that this entire data set is our population, okay? So again, back to our formulas. In order to calculate a z-score, we need a raw score, a mean. In this case, we're going to say this isn't x bar, but rather it's mu to represent a population mean. And then down here, instead of standard deviation, it would be sigma to represent a population standard deviation. Okay, so again, use your imagination. Right, so for a z-score, we need x, we need the mean, we need standard deviation, and that will give us, those are the elements we need to get z, and then we can use our z table to find our percentile. Okay, so figure out what you're looking for, right? And the components you need to get that particular value, right? And using z-scores, we know we can use the table to find the percentiles. Okay, so again, our raw score is 801. Our mean is just going to be the average of this group. Again, imagination is saying, whoa, this whole data set is the population mean, right? And then we need to calculate standard deviation. Okay. So pop this up there. And then we can use this information to find our z-score. So again, we do raw score minus the mean divided by standard deviation. We get a z-score of negative 0.8, and we can round this 5 up to a 6, so negative 0.86 on our z table. We would find negative 0.8, and then 0, 1, 2, 3, 4, 5, 6. So our estimated percentile, assuming that this person is from a normally distributed population, is going to be 19.49%. Now you can see there is a discrepancy in this area. Why? And we'll get this information from looking at a histogram of the data. Okay, so similar to our first student values set, okay, going to highlight all of the data. I'm going to click Insert, Histogram. Again, it's like freakishly small, and I'm so sorry about that. But we're going to make it a little bit bigger. I'm going to add my axes titles, and then I'm going to increase the font size. Just know when you increase the font size in Excel, it like extremely is magnified in Word. So if you make everything big in here and then you copy it into Microsoft Word, it might be like way too big. Okay, remember when you're setting your number of bins, we want to set to 8. If you're in Mac, you click on the bars. If you're in Windows, you click on the x-axis. But I want to format this so that I have a number of bins, and it's 8 bins. Okay. And then you guys can make sure you add your chart title, which you can just call power testing. You'll fill in what your axis title is representing for your x-axis and what the y-axis is representing. Okay. And then you can look at how this distribution is. So there's a question on your answer sheet, and it does involve a bit of critical thinking. Okay. And I think next week I'll go through this visually, but I want you guys to think about it from a critical standpoint. So we say if we have a good sample, right, these two percentiles should be relatively close to each other, which they are, right? 19.49 isn't that different from 21.32. So I could say we have a relatively good sample on our hands. Okay, what calculations can we perform to figure out why we have a discrepancy though, right? Because if our sample, remember we calculated this percentile off the sample, if our sample was representative of the majority of our population, right, and we calculated this value on the basis that we have a normally distributed population, right, the number should actually be a little bit closer. So what calculations could we perform to figure out why we have this discrepancy in percentiles, right? And how do you think the calculation we would use could affect the previously calculated percentiles? And I'll give you a hint here. The reason why these are different is because the sample has this distribution shape, which you can decide for yourself what that looks like, right? And that's what this percentile is calculated off of. However, in a population, and I'm going to try my hand at drawing in Excel. I've never done this before. But in this percentile calculation, right, we were under the assumption that our distribution, oh God, this is already great. We're under the assumption that our distribution is normally distributed, right, with our mean in the center here. Okay, so how does this shape of our sample affect the number that we get of our percentile that this person lands at with this given raw score? Okay, so how does this sample shape, if you think it's similar to this shape, then maybe there is no discrepancy, right? But under the assumption, or making a percentile calculation under the assumption that you have a normally distributed data, how does that differ from when you make a calculation with a distribution that looks like this? Okay, pretty much everyone's going to get effort points for this question because it is a little bit difficult, but just use your critical thinking skills, right? What do you know about certain calculations that are involved in this particular distribution and how they affect the shape of the distribution? Okay, and then how does that shape change based on the distribution we were assuming we got a percentile from? Okay, so this week, your submission list is down here. Okay, so you'll have your completed answer sheet. You're going to turn in your Excel spreadsheet, and you're going to turn in your SPSS output. If you can't remember how to export your output to an Excel file, you can watch the end of the Activity 2 video that was posted last week. You're going to want to make sure you turn it in to Dropbox by 11:59 on Monday the 14th, I believe is the deadline. Okay, if you guys have any questions, whether it's how to do the histogram axes or kind of reformatting the bin numbers, I'm happy to make another video for you, and I can always post it in the discussion area. But just email me if you have problems, and hopefully we can figure things out. All right, good luck.